Neutrino astronomy is the branch of astronomy that observes astronomical objects with neutrino detectors in special observatories. Neutrinos are created as a result of certain types of radioactive decay, or nuclear reactions such as those that take place in the Sun, in nuclear reactors, or when cosmic rays hit atoms. Due to their weak interactions with matter, neutrinos offer a unique opportunity to observe processes that are inaccessible to optical telescopes. The field of neutrino astronomy is still very much in its infancy. The only confirmed extraterrestrial sources so far are the Sun and supernova, SN 1987A. History. Neutrinos were first recorded in 1956 by Clyde Cowan and Frederick Rain from a nuclear reactor. Their discovery was acknowledged with a Nobel Prize for Physics in 1995. In 1968, Raymond Davis, Jr., and John N. Baikal successfully detected the first solar neutrinos in the Homestake experiment. Davis, along with Japanese physicists Masatoshi Koshiba and Ricardo Giacchino, was awarded the 2002 Nobel Prize in Physics for pioneering contributions to astrophysics, in particular for the detection of cosmic neutrinos. This was followed by the first atmospheric neutrino detection in 1965 by two groups almost simultaneously. One was led by Frederick Rain, who operated a liquid scintillator in the East Rand gold mine in South Africa at an 8.8 km water depth equivalent. The other was a Bombay-Osaka-Durham collaboration that operated in the Indian Kolar gold field mine at an equivalent water depth of 7.5 km. Although the KGF group detected neutrino candidates 2 months later than Rain, they were given formal priority due to publishing their findings 2 weeks earlier. The first generation of undersea neutrino telescope projects began with the proposal by Moisey Markov in 1960 to install detectors deep in a lake or a sea and to determine the location of charged particles with the help of Cherenkov radiation. The first underwater neutrino telescope began as the DUMAND project. DUMAND stands for Deep Underwater Muon and Neutrino Detector. The project began in 1976 and although it was eventually cancelled in 1995, it acted as a precursor to many of the following telescopes in the following decades. The Baikal Neutrino Telescope is installed in the southern part of Lake Baikal in Russia. The detector is located at a depth of 1.1 kilometers and began surveys in 1980. In 1993, it was the first to deploy 3 strings to reconstruct the muon trajectories as well as the first to record atmospheric neutrinos underwater. Amanda used the 3 km thick ice layer at the South Pole and was located several hundred meters from the Amundsen Scott station. Holes 60 centimeters in diameter were drilled with pressurized hot water that strings with optical modules were deployed in before the water refreezer. The depth proved to be insufficient to be able to reconstruct the trajectory due to the scattering of light on air bubbles. A second group of 4 strings were added in 1995-96 to a depth of about 2,000 meters that was sufficient for track reconstruction. The Amanda array was subsequently upgraded until January 2000 when it consisted of 19 strings with a total of 667 optical modules at a depth range between 1,500 meters and 2,000 meters. Amanda would eventually be the predecessor to IceCube in 2005. 21st century. After the decline of DUMAND, the participating groups split into 3 branches to explore deep-sea options in the Mediterranean Sea. ANATES was anchored to the seafloor in the region off Toulon at the French Mediterranean coast. It consists of 12 strings, each carrying 25 stories, equipped with 3 optical modules, an electronic container, and calibration devices down to a maximum depth of 2,475 meters. Nemo was pursued by Italian groups to investigate the feasibility of a cubic kilometer scale deep-sea detector. A suitable site at a depth of 3.5 kilometers, about 100 kilometers off Capo Passaro at the southeastern coast of Sicily, has been identified. From 2007 to 2011, the first prototyping phase tested of mini tower, with 4 bars deployed for several weeks near Catania at a depth of 2 kilometers. The second phase, as well as plans to deploy the full-size prototype tower, will be pursued in the KM3 framework. The Nesta project was installed in 2004 to a depth of 4 kilometers and operated for 1 month until a failure of the cable to shore forced it to be terminated. The data taken still successfully demonstrated the detector's functionality and provided a measurement of the atmospheric muon flux. The proof of concept will be implemented in the KM3 framework. The second generation of deep-sea neutrino telescope projects reach or even exceed the size originally conceived by the DUMAND pioneers. IceCube, located at the South Pole and incorporating its predecessor Amanda, was completed in December 2010. It currently consists of 5,160 digital optical modules installed on 86 strings at depths of 1450 to 2,550 meters in the Antarctic ice. The KM3 net in the Mediterranean Sea and the GVD are in the preparatory, prototyping phase. IceCube instruments 1 cubic kilometer of ice. GVD is also planned to cover 1 cubic kilometer but at a much higher energy threshold. KM3 net is planned to cover several KM3. Both KM3 net and GVD could be completed by 2017, and it is expected that all 3 will form a global neutrino observatory. Detection methods. Since neutrinos interact only very rarely with matter, the enormous flux of solar neutrinos racing through the Earth is sufficient to produce only one interaction for 1036 target atoms, and each interaction produces only a few photons or one transmuted atom. The observation of neutrino interactions requires a large detector mass, along with a sensitive amplification system. Given the very weak signal, sources of background noise must be reduced as much as possible. The detectors must be shielded by a large shield mass, and so are constructed deep underground, or underwater. They record upward-going muons in charged current muon-neutrino interactions. Upward, because no other known particle can traverse the entire Earth. The detector must be at least 1 kilometer deep to suppress downward-traveling muons, and is subject to an irreducible background of extraterrestrial neutrinos interacting in the Earth's atmosphere. This background also provides a standard calibration source. Sources of radioactive isotopes must also be controlled as they produce energetic particles when they decay. The detectors consist of an array of photomultiplier tubes housed in transparent pressure spheres which are suspended in a large volume of water or ice. The PMTs record the arrival time and amplitude of the Cherenkov light emitted by muons or particle cascades. The trajectory can then usually be reconstructed by triangulation if at least 3 strings are used to detect the events. Applications. When astronomical bodies, such as the Sun, are studied using light, only the surface of the object can be directly observed. Any light produced in the core of a star will interact with gas particles in the outer layers of the star, taking hundreds of thousands of years to make it to the surface, making it impossible to observe the core directly. Since neutrinos are also created in the cores of stars, the core can be observed using neutrino astronomy. Other sources of neutrinos, such as neutrinos released by supernovae, have been detected. There are currently goals to detect neutrinos from other sources, such as active galactic nuclei, as well as gamma-ray bursts and starburst galaxies. Neutrino astronomy may also indirectly detect dark matter.